Hello everyone. I am Mädälin Neagu, COO and Head of Engineering at Cryptodata. First of all, I want to share with you the fact that this was the most challenging project in my career, and I think all members of the team involved in this project feels the same. It was an incredible project, a lot of work, hard work, but we did it. And for it, I want to thank them and to congratulate them. Please help me to congratulate them. They are among us here. They work a lot and they deserve it. They really deserve it. Further, I will share with you some technical features, insights of our electric concept car. Building an electric vehicle from scratch with all the different integrated technologies required an immense effort in terms of resource management. However, the experience gained from building this concept allowed us to better understand the requirements and barriers associated with this kind of project and helped us improve our operational capabilities in many other fields of activity. We must keep in mind that Momentum claims to be a genuine electric supercar, so it offers impressive adaptive performances. Depending by the circumstances, electric motors are very versatile. The car offers 3 different driving modes and a 4th additional custom mode. It can be used as a normal car for long-range trips. On the other hand, it offers enough fun to drive if you select sport mode, or it can give you an unforgettable experience on the track if the race mode is activated, believe me. Here in this mode, the external battery pack could be removed to decrease the total mass of the vehicle for the race fast laps. Also, you can have a fully custom settings, a fully custom vehicle that can provide up to 900 horsepower by adding in-front electric motor and whatever custom features you would like. As my colleague Ovidiu mentioned before, Momentum was designed as a modular vehicle that can be upgraded easily. It represents a platform that can be used to test and implement new technological concepts, both hardware or software. The prototype in front of you has a tubular frame that meets our requirements in terms of performance, functionality, and adaptability, but we are currently studying a more performant version of carbon fiber monocoque chassis. Also, the Proto number 1 here has rear-wheel drive with an electric motor on the rear axle, but the chassis allows you to easily add the front electric motor, make it a 4-wheel drive vehicle, a proper example for the adaptability and potential, as I said, of the custom mode, offering incredible dynamic performances. But we believe that the key component which will help increase the pace of large-scale adoption of electric vehicles is the concept called smart battery sharing. How it works? We already are in this business for a while, smart battery sharing concept. One of its fundamental aspects is represented by user mobility. Nowadays, all our activities are conditioned by smart devices powered by electric energy. So, for Cryptodata, the concept of smart battery sharing has 2 stages. The first stage is about the implementation of interchangeable batteries designed for smart electronic devices. We began to develop in early 2021, and it is still ongoing process at this time, expanding the network. It's called Bank of Energy. Probably some of you already know about this project. The second stage will be implemented this year within this concept car launch as an extension in automotive industry for the smart battery sharing concept. The concept applied for electric vehicles, I talk about smart battery sharing concept, requires installing additional battery modules which will provide a supplementary range up to 100 kilometers. You can see a maquette here in the rear side of our prototype of this system. This means that the user's mobility will cease to be conditioned by slow recharge times. The module must be easy accessible, handled by a single person, and it functions in a plug-and-play manner that facilitates a quick and smooth replacement. This way we have constant access to energy to keep up with our daily activities, of course. From my point of view, as an automotive design engineer, actually this is my profession, besides the difficulties regarding limited lithium resources, I think that a successful transition toward electric vehicle can only be achieved by eliminating the issue of constant wasting time to recharge. We can simply swap the discharged battery and with a charged one in less than a minute. This project proposes an important change in the industry. The concept of smart battery sharing does not solve the problem of long-distance travel. Still, it does provide the best solution when it comes to short-range, city-bound trips. Therefore, I consider that this project is an essential step for the automotive industry, which will lead to new research and development opportunities in the field of electric vehicles. Now, because I'm the mechanic, I will bring on the smart guy to explain you the technology on board our electric concept car. So, Felix Negoitä, I would like to invite you on the stage.
Good afternoon, everybody, and thank you so much. Thank you, Mädälin. I'm very excited to be here today. My name is Felix Negoitä, and as Head of Artificial Intelligence here at Cryptodata, it is my great privilege and my great pleasure to talk to you today about some of the most exciting deep learning technologies that the Momentum platform was built for. At our Research and Development Division, we believe that the ubiquity of AI is a natural step towards our integrated vision of the future. Now, it is very tempting to dive deep into academic discussions concerning how the future of artificial intelligence will impact our societies. However, machine learning systems at scale are already performing incredible tasks and incredible automation in our computers, in our mobile devices, on our entertainment platforms, and even on the road. So let's take a look at our proposal for intelligent autonomous vehicles. Now, first things first, as our engineering efforts developed, we observed that everything we're striving to achieve can very neatly fall into one of three possible categories. So first off, we have optimizing for traffic, where, of course, we're interested in combining both algorithmic and learned pathfinding techniques with real-time data. Then we have, of course, developing safety behavior by letting the vehicle make decisions relative to its external environment that optimize our well-being. And perhaps most importantly, we have self-learning, the intelligent vehicle's ability to operate within the knowledge domain of its ever-expanding universe of internal representations. So since it all starts with learning, I propose we briefly review that aspect first. Now, it may not be obvious at first glance what we mean when we say learning in the context of a vehicle. For example, many aspects of our daily lives that we take for granted as humans turn out to be incredibly difficult to mathematically model and program machine-wise. For example, driving. Driving involves an intricate connection between our motor functions, image processing neurological pathways that reside in our brains, and the ability to make snap decisions by analyzing our environment and anticipating our fellow drivers. So it is thus a highly complex activity, which is probably why I failed my exam the first time around. But in order to have a machine achieve all of this, the process starts with data gathering, data science, and data engineering. The vehicle needs to work with 3 types of data simultaneously. First, it has to collect all possible representations of its external environment, such as, for example, video feed from its cameras, data from its proximity sensors, data from LiDAR, anything you can think of. Then, it has to keep an internal state of itself in order to be able to make decisions. So that includes anything you can think of, from what your current speed is right now to what the pressure in your tires is right now, for example. And lastly, we want to emphasize the importance of different types of ensemble learning. On the one hand, we want vehicles to be able to share their drive data with one another. This would create a distributed machine learning system where each node benefits from the knowledge of the network as a whole. Now, on the other hand, we envision it going a step even further than that. We envision it connecting the intelligent autonomous vehicles to other devices in real time so that it can learn from them as well. All of these complex AI systems working together will enable momentum to self-calibrate, self-adapt, and maximize the protection of its passengers. Now, you may be wondering, okay, so how does AI achieve all of this? Well, the images the vehicle captures are processed by deep convolutional neural networks which learn internal representations of real-world objects as vectorized features through an algorithm called backpropagation. This is, of course, done with supervised learning long before the car that you see in front of you today actually hits the road. However, the networks have to be pre-trained in order to analyze the images in real time. We also need a sort of a combination of deterministic systems on one hand and machine learning on the other hand for the AV to learn to control itself in its environment. Furthermore, data collected by all the vehicles, as I have previously mentioned, is fed into a reinforcement learning computer simulation whose job is to approximate a Q-learning function of the value of possible actions in a given environmental state. This is how the vehicles learn to drive per se, right? So, however, there's a catch here. As much as we want it, and I know we really want it, but as much as we want it, we are never alone in traffic. Driving is not an action we alone undertake in our environment. It is rather a complex set of interactions that we have with other drivers in that specific environment. So, here comes the problem. If by modern AI we mean the application of machine learning to specific problems, then in order to achieve the different levels of autonomy that we want from our self-driving systems, we need to introduce the meta-modeling of multi-agent systems, which is a generalization of artificial intelligence that describes the interactions between different actors. Although our use case is further complicated by the fact that our system contains a mixture of human agents and AI agents, we fortunately have the mathematical modeling of game theory to help us. It provides a framework within the largest theory of complex systems for choosing strategy and driving towards equilibrium. When the agents have chosen a strategy, they need not change, assuming, of course, the rationality of the rest of the agents. We say that our system has entered the state called Nash equilibrium. For example, this includes stopping at a red light and letting the other agents entering your intersection pass. Cool. So let's talk a little bit about safety behavior. Let's turn towards how the Momentum platform can implement these safety behaviors and what we mean by them. We can use the growing interconnectivity of our digital world to communicate with other devices for a better understanding of our surroundings. The more data the system collects, the easier it will be to minimize the risk of accidents in the decision-making process. Autonomous vehicles that are connected to a shared network and to one another can, quote-unquote, see themselves much sooner than the human visibility field would allow, thus helping avoid unpleasant incidents. Furthermore, as we have previously mentioned, by combining the modeling of game theory with reinforcement learning, we can tell the AI agent to optimize safety strategies by assigning to them a higher utility function within the reward paradigm of reinforcement learning. Cool. Now, there's one thing missing though. We want an intelligent vehicle that by collecting and analyzing the data from your driving is able to model your unique style and to adapt to it, helping the human-AI interface achieve a joint decision. For example, by better understanding that your style is more aggressive, the AI can help anticipate and implement the optimal safety-related maneuvers given the circumstances of your present environment. And now, as Steven Pinker said in his last book, he pointed out that human deciders do not have the luxury of analyzing immense amounts of data and optimizing them before taking a spur-of-the-moment action. They must instead suffice with an alternative that seems something like good enough to them in that split second of a decision. And intelligent AVs, fortunately, can help us change all that. Of course, we want to be able to perform as good as possible in traffic. So we need dedicated intelligent systems for this aspect of Momentum alone. What we call the Traffic Optimizer module represents a series of machine learning-powered analysis. Pathfinding algorithms from graph theory help us determine what the best way to navigate the city is. But by incorporating real-time data from other devices and other AVs, we are able to predict congestion, we're able to calculate alternate routes, we are able to suggest optimal traveling times. It's the intercommunication between the vehicles themselves, which, as I mentioned, is extremely helpful for safety, but however, it can help us, as we have seen, create a more fluid traffic flow and avoid unpleasant aspects such as the phenomenon of phantom brake. Thank you so much for listening to this topic that I'm very passionate about. I will now invite on the stage the one, the only, the legend, Mr. Howard Dell. Thank you so much.
Stop it. All right. Ciao, brother. I'll take the, bro. Yeah, I'm going to give that to you. Thanks, brother. All right, back again. Okay. It is now my privilege to introduce another gentleman, our special guest, a renowned engineer and Silicon Valley entrepreneur. He is the inventor of multiple patents and one of the original founders of Tesla Motors in 2002. Through his activity, he brought major contributions to the automotive industry by reinventing the electric car as a desirable and competitive alternative to the internal combustion engine. After his departure from Tesla in 2007, he continued his career in the automotive industry as the Director of Electric Vehicles at Volkswagen, and is currently part of multiple boards of directors and advisory boards for several Silicon Valley startups. Our special guest, ladies and gentlemen. Put your hands together, show some love for Mr. Martin Eberhard.
Well, thank you very much, and thank you for inviting me. It's great to see new players in the EV revolution, and it's great to look where the EV future is going. For a change, I'd like to spend a few minutes and tell you a little bit about the EV past. I'd like to show you a little bit how the EV revolution started. It started with this car, the Tesla Roadster. So we started off not looking to make electric cars, but rather to solve this problem. In 2002, there were almost 1 billion cars in the world, and predictions are 2.4 billion cars by 2050. And it seemed clear even then that we just can't power all those cars with oil. It just can't be done. Okay, so if not oil, then what? So again, I didn't start off looking to make electric cars. I wanted to make a car that just didn't use fossil fuels or used a lot less. So I looked at every kind, all of the different possible ways you could power a car. And I looked at them this way. What is the resource consumption for each of these technologies per kilometer? And the conclusion, of course, that I came to was that electric cars are the best choice. I'd like to walk you through that thinking a little bit, just to show you how we did it with one example. Are electric cars really better? So if we took a pretty good gasoline-powered car, 9 liters per 100 kilometers, and we know what is the energy content of gasoline, and we know what is the conversion from crude oil to gasoline. And from this, we can calculate that this car will use about 1,000 watt-hours of crude oil energy per kilometer driven. The best you could do in 2002 was, with a hybrid car, was maybe 670 watt-hours per kilometer. If you compare that to an electric vehicle, let's just say we power an electric vehicle using electricity that's made from the worst coal-fired power plants in the world. Okay, we know the electric vehicle uses about 155 watt-hours per kilometer. We know the efficiency and the energy content of coal, and this is a pretty crummy coal-fired plant. It's 29% efficient. That vehicle is still equivalent to a gasoline car, but we can do better with a modern coal-fired power plant. This is only 489 watt-hours per kilometer. And of course, natural gas is even better. So if you stack it up, what you see is that the best you can do with gasoline is just about the same efficiency as the worst you could do with an electric car using fossil fuels. If we try a little bit harder, either with a modern coal-fired plant or with natural gas, the electric car is dramatically better. And of course, for electric cars, you don't need to use fossil fuels at all. And as an example, I'll show you this. This is my car, and that's the solar panels on my roof. All right? And that panel powers my entire house and my car. So just as an example, my electric bill every month is about $11 per month. Okay, so the conclusion was that electric cars really are the best choice. So what was going on in the world? In 2003, no car companies anywhere in the world were making electric cars. And there was two things that everybody knew about electric cars. First, they're dead, and second, they suck, right? That's what everybody knew. And why was that? Well, because this is what people thought electric cars were like, right? They're awful. They're not the kind of car anybody wants to drive, right? Electric vehicles didn't appeal to car buyers, right? What appealed to car buyers were these, sports cars like this, right? It's exact opposite of what the electric cars that came before looked like. EVs were not sexy. Okay, another conclusion, of course, is that past EVs were really, really low tech, the exact opposite of what you see sitting in front of you. They were simple lead-acid batteries, simple DC motors. Often they're just converted gasoline cars, or even worse. So the number one radical idea behind Tesla was to revive the EV by making a real sexy sports car instead of what had been made before. This had never been done. And that's what we set out to do when we started Tesla Motors. This is half the company right here. The other half of the company was holding the camera. Yeah. And so I'll walk you through some of the early challenges we ran into as we're learning how to create a car company. And the first, as I mentioned, was that the public perception of EVs was terrible. The next big thing we ran into is that the entire automotive industry is not made for small car companies. All of the equipment, all of the manufacturing processes, everything was made for either really, really high volume or one-off single, like, race cars. And related to that, suppliers just don't want to sell to small car companies. And the worst was, for me, was the airbags. The airbag suppliers said to me, the number of airbags you want to buy is like a prototype run for us, and the liability for us is just not worth it. So it took every single safety component was an argument with a supplier to get them to provide these parts. Somewhere in the early stages of Tesla, it started to become clear that the claims of safety that the manufacturers of lithium-ion batteries were telling us were not true. That we had these spectacular laptop fires, maybe some of you remember these, and it caused us to think a lot harder about how to make a battery pack safe. Vehicle validation, especially crash testing, is crazy expensive. Every one of these crash cars that we built cost us about $350,000, and that was 20 years ago. So here's some of the things that we did to make Tesla happen, starting from that background. First of all, we designed it, as I said, as a real EV sports car. We engineered the Roadster for performance from the beginning. We designed it to look like a sports car. That's a clay model they're building out of this pre-CAD, right? The next radical idea was to use commodity lithium-ion cells to power the car. These are the kind of cells, the exact kind of cells that were being used in laptop computers and were being used in camcorders. And this seemed insane. Instead of 4 cells in your laptop, we had nearly 7,000 cells in the car. But the reason we did that is because at that time, there was no such thing as an automotive lithium-ion battery, right? This is what was being mass-produced. The next radical idea was to use a DSP-controlled AC induction motor. This is a high-tech drivetrain. And by the way, the AC induction motor was invented by Nikola Tesla. This is why I named the company Tesla, was for this reason. In the beginning, it was not possible for us, in our small group of Silicon Valley engineers, to design the rest of the car, the suspension, the safety systems, the bodywork, and so on. So we partnered with Lotus in the UK because they had a history of already doing consulting work to other car companies. And they made a car that was already street legal for sale in the US, so the safety systems of that were carried over for our car. So the first thing we did is we took a Lotus and tore it to pieces and turned it into a mule for our car. This was kind of fun. We took a brand new Lotus car and took a Sawzall and cut it up and turned it into our car. It was the first cut was difficult. We opened an outpost office both at Lotus in the UK and also in Detroit that allowed us to hire about half of our team from the auto industry. So we had this blend of engineers from Silicon Valley and engineers from the auto industry. And it was definitely a management task to get these two teams to work together collectively, and we did. We built, staffed, and funded a real battery research and development lab and learned how to build these battery packs with 7,000 cells in them. And we built a factory to build these battery packs. Similarly, we figured out how to make our own motors, and we built a factory to make our motors. It's expensive, and I was not a rich guy, so we raised a lot of money from other people. You might recognize that guy, our first large investor, who now is the CEO of the company. But it worked. The 2007 Tesla Roadster broke all records for electric cars, 0 to 60 miles per hour in 3.9 seconds and a range of well over 200 miles. And in contrast, no electric vehicle had been made before that could even do 100 miles range. So in 2003, the electric car was declared dead. And 2003 is the year that we founded Tesla to revive the electric car. By 2017, all major OEMs were again, or finally, selling electric cars. And today, we're at the point where EVs are almost the same price as a comparable gasoline car. I think it's a couple of years and it'll be actually cheaper to buy the electric car than the gasoline-powered car. So I want to put this slide up. This is a slide from my old slide deck from 2005. And I used to put this up in the US and say the need to get off of fossil fuels was an issue for both ends of the political spectrum. And I would put this up and say, one of these pictures, this is Al Gore, of course, and his climate change, and Condoleezza Rice and her concerns about national security. And I said, you probably relate to one of these pictures, and the other one pisses you off. And it doesn't really matter which one. Both of these are good reasons to switch from fossil fuels to an electric car. And I just as a point here, this is the same slide, just different pictures. I think that these issues are, if anything, more important now. Global warming is more obvious, and the national security issues with buying our large quantities of our fuel from other countries is dangerous. So, as I say, for increasingly obvious reasons, we really must break our fossil fuel addiction. And the good news is, EVs are actually better anyways. So, with that, I say, mulțumesc. Thank you.